Alright, it's motion in two dimensions part 2. We've been mainly focusing on projectile motion because it's probably one of the more common problems that you're going to see on your homework, and it's a good idea to kind of grasp and understand. I have actually used, a lot of people say they never use math in their daily lives. I have used projectile motion math before. It's pretty useful. To figure out, like, if you were to fall from a certain distance, how fast would you be going when you hit the ground, pretty much anything, everything from silly things like that to rocket scientists, they use this stuff too. So the idea here is that I've got gravity pushing down everywhere with an acceleration equal to g. And you'll notice here that one of the most important things in a problem like this is to pick your orientation. It's really totally up to you. But in math class we've been doing this for so long. So I'm going to say that right is positive and that up is positive in the y direction. But now you could pick these all upside down and reversed or jumbled up. As a matter of fact, you're even allowed to tilt it, but that would just make your life a living hell. You always tend to want one of the axes at least, how would you say it, perpendicular to gravity. Because remember we talked in the last video that the x component of velocity never changes. It's not affected by gravity. And so it's nice to have one axis that is totally unaffected by gravity and another axis that is totally affected by gravity. So that's what we're going to do here. So I've got this problem. It states that on Earth, assuming flat ground, how far will the object travel in the x direction before it hits the ground? And the assumption is that the initial, well, not the assumption, one of the boundaries is that the initial velocity here, this vector that I have drawn, is equal to 5 meters per second. Not 4 meters per second. Alright, so 5 meters per second is the initial velocity, and this angle right here is 45 degrees. You could call that the altitude angle, because altitude is pointing, further up into the sky. And so the first step, just like we discussed in last video, is to break VI into components of VIY and VIX. And we went over that in the last video, so we want to find VIX, the initial component of velocity in the x direction, is equal to, let's see here, it's going to be VI cosine theta. And then, and actually I feel like I should not put a vector sign over VI because I'm actually just taking the magnitude of VI and the cosine of theta, and then of course this is going to be in the x hat direction because it's VI sub x, but I'm not notating the x hat because I'm notating it down here. This is my initial velocity in the x direction. It's equal to the magnitude of VI cosine of theta. And similarly, VIY is equal to the magnitude of VI times sine theta. Let's go ahead and calculate those out and get a good approximation. Alright, so our angle is 45 degrees. Cosine of 45 degrees is root 2 over 2 times the initial velocity of 5. That's giving me 3.54 roughly. 3.54 meters per second. Alright, so what's interesting is with a 45-degree angle, the y component and the x component are equal, because cosine of 45 is equal to sine of 45. So I'll go ahead and plug it in anyways. It still equals root 2 over 2 times 5. It's going to give us approximately 3.54 meters per second. So those are our initial velocities in the x and y direction. Alright, so one of the most important things to do in projectile motion is to figure out how much time this thing's going to take. by starting in the y direction with this equation. This is probably one of my most used equations for projectile motion. I always like to start in the y direction if I can and use that to solve time. Because here's what's cool. It doesn't matter whether there's an x component of velocity or not. As long as the y component of the initial velocity is the same, it will take the same amount of time to hit the ground. Example would be if I toss something like this, or if I toss something like this, or even if I just threw it straight up and down. You'll notice that as long as the VIY component, the velocity initial in the y direction, is the same, all of these projectiles will reach the same height, regardless of the x value of velocity. And so that's a fantastic thing. So what that means is that we can completely ignore the x component of velocity for now and just solve the y. And so in order to do that, I'm going to go ahead and take this equation for the y direction, so 1/2 a sub y t squared plus vi sub y, the velocity initial sub y times t, plus y initial equals y final. And we know that we're starting at y equals 0 and we're ending at y equals 0 because we conveniently chose our origin to be at the true origin of our Cartesian coordinates. So we start at 0 and we end at 0. And we know vi sub y, we just calculated that. Vi sub y is 3.54. We still have time multiplied by it. And we know ay. We know ay because it's the same everywhere on the surface of the Earth. It's equal to g. And g is equal to negative 9.8 meters per second squared. The reason why I say negative is because I chose up to be positive, and g is acceleration acting downwards. So if I chose positive up, then g is negative, and that'll be important. You'll always want to make sure to match with your convention, otherwise you'll end up with some funky answers. So we have 1/2 times acceleration in the y, which is negative 9.8, times t squared, all of that equal to 0. So we can subtract negative 3.54t onto this side, and over here we still have 9.8 divided 2 with a negative sign in front of it, so that's negative 4.9 t squared. And now we can divide both sides by t. T's are going to cancel to 1 here, and here it's going to cancel to just a t to the power of 1. So negative 4.9t equals negative 3.54. Negatives cancel. We can multiply both sides by a negative, and then we'll divide both sides by 4.9. So 3.54 divided by 4.9 gives us a time that is approximately equal to 0.722 seconds. All right, so 0.722 seconds is what we have going on for time. All right, so now that we have time, we can now go to our original idea, right? So we know that v is defined as the change in x with respect to time. We're looking for the change in x, right? So we could multiply time over here and say v times t equals our change in x. Which v would this be, though? Would this be, because we're interested in the x direction, right? So this is going to be v in the x direction. And it's actually going to be our initial v, too. Like I said, this the VIX component of velocity will always be the same length because there's no acceleration acting on it. So VIX times t equals delta x. Well, we know t, we just solved for it. We know VIX, we solved for it up here. So we just take those two things multiplied by each other. 3.54 times 0.722, and that will give us the answer that we're looking for. And that's roughly 2.56 meters. And so that is this distance right here on an x-axis. I hope this was helpful. Yeah, if you're curious why I use this instead of a kinematics equation, it's just because this is the definition and it was easier to use because these are for constant acceleration, and in the x direction here it was constant velocity. So instead of using one of these equations, which I could have used one of them, instead I just opted to use the definition of velocity, which is a change in x with respect to time. So I hope this was helpful, and I'll see you next video.